Good afternoon. My name is David Fries, and this is the BESA webinar. And you can tell it's a special day today because I'm wearing a tie. We only wear a tie for ministers, dames or sirs, or audiences over 500. And this is the first time I've worn a tie for a very long time. Present from my daughter. In fact, I forgot I've still got the label on it, but it feels kind of good. So our guest today, very special guest, Professor Cath Noakes, who's Professor of Environmental Engineering and Deputy Director of the Institute for Fluid Dynamics at the University of Leeds. Good afternoon, Cath.
Hi, David.
Hi. I'm just waiting to see your camera come on. Hi, yep. Welcome. We were talking before you came on. How different is your days or your weeks now from what it was a year ago? Surely it must be very different.
Yeah, something like that. I mean, yeah. Who'd have ever thought that ventilation would become quite so high profile? And yeah, I overwhelmed with work, I think, is how my days are now. But I think it's still important to take time out to do these types of webinars.
Well, that's very kind of you to do that. As we said, we've got a big audience, a big mix of audience, from academics to contractors to clients, insurers across the piece. So we're going to have a short presentation from you, and then we'll do Q&A. If you have questions, get them in now, because we've already got a lot. No good giving me them 10 minutes before the end or 10 seconds before the end, because you won't get on. I'll leave you now. See you for the Q&A.
Okay, thank you very much. So hopefully you can all see my screen. Okay, so thank you, David, for the introduction. I'm going to talk about some of the science of what we know about the transmission of COVID and, well, the virus, the SARS-CoV-2 virus that causes COVID-19 disease. And hopefully that will be, and some of the thinking around why we need ventilation to control it and some of the challenges in there. So what do we know about transmission? Well, so far we know it's a respiratory disease. So the transmission is all associated with people's emissions due to respiratory activity, and that can be in the form of aerosols, small droplets, much larger droplets, and even things like secretions. We forget those a little bit, but you know, you wipe your mouth with your hand, you cough into your hand, you contaminate your hands. And then that means we've got different routes of transmission. So we can have that transmission via aerosols when people are typically more than a couple of meters away, long range aerosols in a shared room. When people are very close, then transmission is complex, it's difficult to unpick, but it's a mixture of a whole different size of aerosols and droplets. And then there is potential that we have transmission via surfaces too, through contaminated hands and touching eyes, nose and mouth. And even just looking at this diagram, actually you can see that there's some complications in here. We're dealing with a disease where there are 3 or even more transmission routes, which are all a complex interplay of people and their environments. We also know a number of risk factors. So there's good evidence that being closer to somebody increases your risk. It's quite likely that when you're face to face, it also increases risk because you're more directly exposed to their exhaled breath. We know there's good evidence that risk is much higher when people are indoors, and we think it increases with poor ventilation. It's hard to exactly pin that down, but there's evidence pointing in that direction. We also know that risk is likely to increase the longer you spend with somebody, particularly if you're very close with an infectious person, and that's why household transmission is a particular concern, simply because you're spending a lot of time in the same environment. And then there's evidence that suggests that certain respiratory activities, vocalization activities, make risk higher. So when people are singing, speaking loudly, they're generating more aerosols, more likely to cause transmission. There's also some evidence from exercise classes which suggest that those which are more aerobic with a higher breathing rate are more likely to result in transmission. Crowding is it doesn't so much affect your individual risk beyond the fact that there's a higher chance that there'll be somebody infectious in that environment with you. But then crowding enables greater level of transmission, so it is a big issue from a population level perspective as to how this disease transmits more widely. And then we know it survives better in cooler places. It survives better at low humidity, below about 30 degrees. It seems to survive at 30% relative humidity, seems to survive better. And we also know that in bright outdoor sunlight in the middle of summer, the survival is significantly shorter, a matter of minutes, compared to when indoors which is without the high levels of UV, where it can survive for hours. And then we also know that it's very difficult to pinpoint people who are infectious. People pass on this disease before they show significant symptoms. So that may mean they remain asymptomatic, or it may mean before they are actually showing any symptoms. So you don't have to have a cough and a fever to necessarily pass the disease on. So all of these things actually make life quite difficult, because it's, the virus thrives where you put people together. The evidence that we've got is all quite mixed. So we get the evidence from a whole range of different sources, including things like ONS surveys, from the test and trace type systems, through outbreak investigations, and through lab and mechanistic experiments and models. We do know from animal studies that both air and surface routes are possible, but we can't quite separate out yet how much the air matters versus the surfaces. It does seem that through air is more effective, but we don't know what droplet sizes matter most in those animal studies. Good consensus that it's highest risk in close proximity. It does seem that the sort of random surfaces, you touch a surface in the supermarket, that there doesn't seem to be very much evidence that transmission happens that way. It's not to say it can't, but it doesn't seem to be driving transmission. So if there is anything from surfaces, it's very likely that it's from those that are immediately surrounding an infectious person. We have also seen super spreading outbreaks, so we've seen a number of these. It's quite likely that the air plays a big part in that. What we don't know is how frequently these matter. Are these incredibly rare events, or are these really quite significant? And the problem here is a reporting bias, in that you are more likely to identify and detect these very large outbreaks rather than the routine sort of what's happening on a daily basis, and they do then get over-reported. We also know that where airborne transmission possibly does happen, it's associated with very poorly ventilated spaces. So most of those where it has been flagged, we're in the sort of region of 1 to 3 litres per second per person. There's very little evidence to suggest that airborne transmission is happening where we've got 10 litres a second per person in a space. And I'll talk a little bit about air conditioning units further on, but there are some evidence that they might play a part in it. I've already mentioned outdoor transmission. There's very little evidence that it happens, and where it does, it seems to be in crowded places where people are close together. There is no evidence that I've seen about transmission over a longer range outdoors. Having said that, it might just be we can't detect it, so we always have to be careful that we don't assume things. And then I think this is where it comes on to the very last part of this slide. Transmission can happen anywhere. We like to say, oh, a school is risky, or a hospital is risky, or an office is risky. It can happen anywhere where you put people together, but some risk factors make some settings more or less risky. So if you have people there for long durations, they're not wearing face coverings, they're talking loudly, they're interacting closely, all of those things add up to risk factors that make that setting more likely. I should also highlight as well that transmission is not always what it seems. So it's very easy to see there's an outbreak associated with a particular workplace and immediately think, oh, well, that workplace must be badly designed, badly ventilated. But when you start going through the detail of those outbreaks, often what you find is some of that transmission happened within the workplace itself, but other transmission happened because people travelled in cars together to get to work, or socialised together, or lived in the same house together. So there's always a little bit more to it than it can immediately look, and we always have to bear that in mind. Let's go back onto the how it transmits and thinking through how this happens. So we've got our source of transmission. That might be a cough, it might be a sneeze, it might be breathing, talking. In a hospital setting, it could be to do with treatment. Whatever it is, it's creating a particular distribution of particles carrying virus, and that will happen, be emitted from that person over a particular duration of time and for a particular location. They may only emit for a very short period in a particular place, or they may be emitting for a long period of time. Once those particles go in the air, they get transported, they will deposit. It will depend very much on the airflow dynamics and the particle size, and then ultimately expose people. And that exposure might be through smaller aerosols which are inhaled, the larger droplets which hit people's mucous membranes, and then surfaces and fomites. And the whole thing is really complicated. So it's this whole complex interaction of microorganism, human characteristics, and the flow and airflow dynamics in that space. We've got a little bit of evidence of where it has been found in the environment, but it's quite hard to rely on this because it's quite sporadic. On surfaces, it can persist as RNA for quite a long period of time, several days. Doesn't necessarily mean it's infectious. In the air, it won't persist because it will only be in the air when somebody's infectious is present in that space, and for maybe half an hour or so afterwards, depending on the ventilation in that space. So if you go and try and sample in the air, it's actually quite hard to find it. You know, you've got to be there right at the right moment in time to capture it. But there is studies that have found it on surfaces. There are studies that have found it in the air. Very few of these studies have managed to culture any of the live virus, but there is, I think, maybe 2 studies now that have cultured live virus from the air, and 1 or 2 that have cultured it from surfaces. Most of this data is from hospitals, and there's very little from the community settings. Also, an awful lot of this is relatively early on in the pandemic, but there is more and more data starting to appear now. But it's actually very hard to do this sampling, hard to do it accurately. There's a lot of differences between sampling methods that people use, and you know, that might be what a lot of the reasons why we're not seeing the environmental detection. Just to go back to then the respiratory aerosols, the virus itself is only about 100 nanometers in size, but it's not a naked virus. It's contained within respiratory fluids. So we're really mostly interested in those particles that are in the sort of 0.5 to maybe up to 100 micron size. Those are the ones that are going to pose the greatest risk. The diagram on the right just shows some typical data of what people produce when they talk, and the size distributions. But those particles will evaporate, will depend on the environmental conditions. But some of these things are likely to deposit, but the smallest ones will be controlled by the room airflows. So it's a very complicated picture here. We know that there's a massive variation with activity, and this is just some data looking at particle generation from people, from a study carried out by the University of Bristol. What you can see is that as people are singing, you get an increase in as they increase in loudness, you get an increase in the number of particles. Same with speaking. If you speak loudly, the highest volume speaking and singing are similar to coughs. But I want to draw your attention to the breathing. And if you just look at the distribution, how big a distribution. So even just different people, some people breathe out hardly any particles, some people breathe out a huge number. So this means we can't just say, you know, everybody's the same. We all breathe and speak out different numbers of particles. We also have to bear in mind that particles are not viruses. So we need to relate these 2 viruses. We don't yet have data for the SARS-CoV-2 virus, but we do have some data for other pathogens. This is collected by Professor Don Milton in the US, who looked at the influenza virus in different sizes of particles. And again, what you can see in here is he found it in small aerosols, less than 5 micron. He found it in larger aerosols, more than 5 micron. You can see that you get a bit of an increase as people are coughing in here, but you also see an enormous range again. So some people produce very little, others produce a great deal. We really need this type of data for the SARS-CoV-2 virus because we don't know if we'll see the same patterns appear in that or not, or whether it might be more in the coarse or more in the fine fraction. We don't have that data yet. So once these aerosols are in a room, we need to think about where they go. And this is, again, the complexities of the fluid dynamics of it. When you're very close to somebody, you're going to be exposed to much higher concentrations of all particle sizes, both the small aerosols and the larger droplets, which will deposit out. When you're further away, you're going to be exposed only to those smaller aerosols that are able to stay in the air for long periods of time. And how this happens is a complicated mix of all of the flow patterns that happen in that environment, most complicated in the vicinity of the person who's infected and their exhaled plume of air. So thinking about the engineering side, as this is what most people in this space do, in all of these spaces, we should be thinking about applying this hierarchy of risk controls. So actually trying to prevent the people being in the environment, trying to prevent the infection being there in the first place through elimination and substitution methods are critical. But then this is where we come in, and this is the engineering controls, which sit above those controls which rely on human behaviour. So all the things like cleaning regimes, marking spaces out, even wearing face masks, all of those rely on human behaviour. And if we can get the engineering controls right, we provide a base level of protection that then supports through for other methods to be used. So we shouldn't be totally reliant on the human behaviour aspects. And that range, the engineering controls obviously are very significant, but we also need to think, where do these controls matter in the diagram of transmission? And I know this is quite a messy diagram, but we need to recognise that some controls will act against more than one transmission route. So face coverings can act against multiple transmission routes, albeit they're very dependent on human behaviour. Cleaning can only mitigate the transmission routes via surfaces and hands. Ventilation can really only mitigate the transmission via the very smallest aerosols. And the larger aerosols, and when you're very close to somebody, can really only be mitigated through physical distancing, face coverings, and potentially screens if they're designed correctly. So we need to think about making sure interventions sit in the right place and block. We need to know which transmission routes they're blocking. So from an engineering perspective, the major one here is going to be about controlling airborne risks through ventilation. And that's not just simply as saying we're going to ventilate. There's an awful lot more to it than that, including how the air distribution, the pressure, the different temperatures and humidity, etc. But we also do have virus inactivation technologies, and particularly of importance here is the air cleaning technologies. So how can we assess this exposure? What do we know about it? So again, another picture shows just that massive complexity of what happens in a real space, but we can simplify some of this. So we can do some fairly simple mathematical models to say, okay, well, if we've got an emission, we've got a ventilation rate, we can calculate what happens in a space over time. We can start with an assumption of a fully mixed space, and we can then start to say, well, how can we look at the role of different interventions in here. In doing this, we need to think about some ventilation metrics, and this is actually a really complicated picture, and I don't think we've properly bottomed this out yet. But thinking about which ones matter the most. Do we talk about the whole volume flow rate? Do we talk about the air change rate? Or do we talk about things which are more personal? And I think for the virus transmission, it's the more personal ones around flow rate per person, or CO2 concentrations that matter the most. And of course, CO2 concentration can be used reasonably effectively in some spaces to give a proxy for ventilation. And the picture on the right shows occupancy in a lecture theatre, and the measured CO2 concentration behaves absolutely beautifully. But if you measure that same thing in a room with only 2 or 3 people, you'll get a lot more variation and a lot more spikes in it. And then just to show that it's not as simple as just saying a ventilation rate either. So the size of the space matters. Again, this is a theoretical model, but this is to say, well, what concentration of virus would be in the air? I've done it as relative concentration. So it's on the left is an office type space where we've said, well, the ideal maybe is 10 litres per second per person. How much would the concentration in that office change if we change the ventilation rate? So if we halve the ventilation rate, obviously a steady state, we would be doubling the amount of virus that you might be exposed to in the air. But it takes time to build up. And in a very low ventilated space, what you find is obviously you get a very high steady state concentration, but it takes a long time to get there. So actually, if you're only in this space for a few minutes, there's very little difference between them. But as you spend more time there, that ventilation rate starts to matter even more. But take us into a big space, and sports halls are pretty popular at the moment for vaccinations and things. We can have quite a lot of people in a very big space, provide the same flow rates, and provide now actually a very low air change rate, but your relative concentration is much, much lower, simply because that very large space provides a huge amount of dilution for that virus, assuming that space is well mixed. So when you're still close to somebody, it won't work. So we need to be quite careful about actually just saying, well, there's a single number in here, a single air change rate or a single ventilation per person, because those relative concentrations you'd be exposed to are going to be really quite different depending on the size of the space. So I think it's telling us we need to be thinking about different spaces differently and a bit more bespoke consideration of the risks. And actually we've started to look at this. So we've got quite a nice model here where we looked at the risks, relative risk of exposure from virus in the air under different scenarios. And here it's not just the space, it also considers the duration of time that you'd be in that scenario. So the reference, it's all relative to a reference space, which is a classroom, which would be designed to a standard of 1500 parts per million. You can see as you change the CO2 concentrations in the classroom, this one's 750, 1,000, 2,000 and 5,000 parts per million, you would get some changes in the relative risks. Offices are very similar because again it's a similar type of ventilation over a similar period of time. But even something like visiting a coffee shop or visiting a supermarket come out quite low. And even the reason being is that these spaces, people are only in them for very short periods of time. But then if you take, for example, the Skagit Choir, which was a very well recognised outbreak, that comes out incredibly high because we've put a number of risk factors together, including very high vocalization in that space. That was relative risk. Can we do absolute risk? The answer is I think the jury's still out on absolute risk. There are models we can use. The problem with a model of using there's a Wells-Riley model which you can use, and it requires data on the infectious dose, and you need a certain amount of outbreak investigation data to calibrate this, and I don't think we've got enough of that yet. We've kind of only got the extremes in here, and what you can see is, even in this very simple model here, it's a bit complex, but we've got ventilation rate along the bottom, we've got percent of people infected, and we've got different levels of infectious quanta which are being emitted. And you can sort of see that you could go from almost no risk in a space to having sort of 80% of your people infected, depending on the emission rate of a person and depending on the duration of time spent in a space. So it's very hard to get to absolute risk yet with this disease. I've talked very much about fully mixed models there. We know that real spaces are much more complex than that. They are connected. We've got air distribution between zones. We've got air distribution patterns. We might have displacement ventilation. If we've got naturally ventilated spaces, we know that these are incredibly variable. And we know that there's also influence locally from people and heat sources. So it's actually quite difficult to specify a ventilation rate. It's even more difficult because we know that it's actually very hard to measure this. So it's all very well if I said, yeah, aim for 10 litres per second per person, but then how do you prove that a space has got that? If we've got a mechanical system, we can do a certain amount of that through measuring the grills with a bolometer or similar. It's quite hard to do tracer testing in real environments. It is possible. And then CO2 is quite commonly suggested as a proxy, which is useful in some spaces, but I think it's only ever a guide. It's very difficult to relate this to an absolute certainty, and it's going to be dependent on the people, their activities. Some people breathe out more CO2 than others, so spaces with small numbers of people are quite variable. The flow rates, even then thinking about the accuracy of sensors and how we can compare between them. So there are a lot of challenges in here, and I think some of the things that as a sector we'll have to think about more over the coming months and years as to how we do this more effectively. I'll just give you an example of some of the complexity. So this is actually a research study where we were looking at understanding natural ventilation. And we set up a full-scale experimental study where we've got a metal cube that's ventilated, has windows in either side of it. And then we set it up on its own, and then we set it up with an array of buildings around it, which were built out of hay bales. You look at the car at the back, you can sort of see the scale of this. So a full sort of representative of a full-scale sort of city environment. And we also did a set of computational fluid dynamics models to look at the ventilation of this. And I wanted to just show you these, not because of the detail of the data. The grey dots represent all the measured data. So first of all, you see the grey dots are hugely variable. And then the red and blue represents the modelled data. The first one on the top left shows the cube on its own with ventilation as a cross flow, so windows open at either side. And what you can see is, depending on the wind angle, you get a really big variation in the ventilation rate. So the ventilation rate's on the left-hand axis. Really big variation depending on the wind angle. Take that same cube that's ventilated with a cross-flow ventilation, put it into an array of buildings, you see slightly lower ventilation rates, but it's a bit more consistent, albeit there's then more distribution on it. Take that same isolated cube on its own, shut one of the windows so it's now single-sided ventilation, we get a drop in ventilation rate and it's a little bit more even. And then take that same cube that's now single-sided ventilation and put it into an array of other buildings, we get the lowest ventilation rates, but we get the most consistent and the least variation with wind angle. So just as an illustration of how variable ventilation is, just through opening windows, it's going to vary massively depending on your design of building. And just to look at this in a bit more detail, that only considered the ventilation rate. This then considers the local distribution. We're putting 6 air changes an hour into this space, but you can see we've got 3 different designs. We've got one which is open on the bottom left, and then the top right has partitions, and then the bottom right has a sort of an aisle down the center of this space. And just to illustrate that if it was fully mixed in here, we would be seeing sort of yellow color all the way through. And the fact we're not, in fact, you see in pockets of higher and lower ventilation rates tells us that that space is not well mixed. And particularly one where you've got a center aisle, you've got a whole zone which gets blocked by the structure in the middle of the room. So, you know, we need to be thinking about this, the mixing of ventilation, because this is going to be important too. I said I've mentioned air conditioning units. There are a couple of studies which have highlighted the potential role of air conditioning units. So the study on the left, this was published fairly early on in the outbreak, and this is from China, just about a year ago, actually, almost to the day. 10 people infected in a restaurant. The people in the rest of the restaurant were not infected, and it was highlighted that there was air conditioners that were creating a particular zonal flow in part of the restaurant, and this may well have done two things. It may well have kept larger particles airborne for longer, but it may have also just continuously redistributed air in one particular part of the restaurant. A key thing with this one is, although it was very much blamed on an air conditioner, when you looked at the actual ventilation rate of the whole restaurant, it was almost nothing. They basically had one extract fan for the whole restaurant, and it was around about 1 litre per second per person, so very, very low actual ventilation rates. Another much more recent one from a Korean study, she showed that people were infected within 5 minutes, and in a very directional position, which from an air conditioning unit, and that really is suggesting that it is quite likely it was maintaining larger droplets which are carrying more virus to be airborne for longer, and then people were able to inhale those larger droplets. I want to finish up by just talking about air cleaning, because I know there's a lot of interest in this. There are huge numbers of different technologies in here for different types of air cleaning, and we need to really think through what the purpose is. So the purpose is removing and inactivating the microorganisms. It's not a reason to reduce ventilation. It's a reason to actually mitigate where you can't ventilate effectively enough. There are systems which are designed for occupied spaces. So some of these systems are applied within the HVAC system or as a local standalone device in a room. Others are designed for unoccupied spaces. And I think they are very, very different. They are for decontamination, and there are very different considerations in there. As far as the technologies go, there's fairly good evidence for HEPA filters for UVC. Far UV looks promising. Some of the other technologies may well inactivate virus, but there are bigger risks that they cause additional problems. So I think with all of these, there are a lot of questions that need to be asked. As in, what's the real efficacy of it? What's the evidence for it? We have very little evidence for real world reduction of infection through any of these technologies. I suspect the only one is some of the UVC studies on tuberculosis and influenza, but very, very little real world evidence for reduction of infection. An awful lot rely on lab data or proxy data. I think when looking at these, there are some considerations around, are there additional benefits? So are they energy efficient? Actually, it might be more energy efficient than vastly increasing ventilation rates. And do they actually improve other aspects of the indoor air quality? Can they remove other pollutants that you might be present to? But it's very important also around what are the risks. So what are you exposed to because of these? Is that exposure to UV light because of a bad installation? Is it exposure to secondary pollutants like ozone or ultrafine particles, which some of these units are likely to generate? And who's exposed to them over how long? I think the other risk to consider is if you put one of these in a space, do people treat it as a magic bullet and believe they are now protected and forget about some of their other the other mitigations that they need to apply? I do want to just touch a bit more on the detail of air cleaning devices. So do you apply it in the ventilation ducts or in the room? If you apply it into the supply air in a hospital type setting where you've got very high risk patients, this can be quite effective, particularly if you're protecting them against environmental microorganisms. It could also potentially be effective where you've got recirculating systems in buildings, and of course some of these devices actually have additional benefits in terms of the performance of the HVAC system. So UVC, for example, will keep a cooling coil cleaner and potentially improve your system. But they have very little impact where there's contaminant sources in the room. So If one person in the room is going to affect another person in the room, it really doesn't matter that much if the supply air is clean, if the source of the contaminants from the person in the room. From an in-room perspective, they are in-room devices are much better suited to dealing with that local contaminant and being able to reduce the local transmission, but of course they don't impact on anything to do with what's taken back through a ventilation system in a building. Those systems that are in rooms, again, there's a lot of decisions to be made in here. We've got sort of portable units, which are consumer units, plug them in, move them around. The risk, I think, with those is that people move them out the way, forget about them, kick them over, position them badly. I would always be a bit more in favour of installed systems where you've actually thought about the design, you've thought about the positioning, you've thought about how it's going to interact with the air flows in the room, and provided a properly sized unit accordingly. It then also means that the maintenance of a device sits with the building services rather than is reliant on an individual to change the filter in their own office, or a teacher in a school, do they change the filter? Who does that? So I think it is probably better to have the installed units. Single pass units are basically, at the most simplistic level, are a box with a fan in it that draws air through that box, passes it through some form of technology, and inactivates microorganisms. Many of these have a really high single pass effectiveness. They will kill 99.9% of what's in there. The real trick here is to persuading the air in the room to go through it. So both the installed ones and the portable ones can be very effective. Again, some technologies will put things out in the room, but we have to be careful that they don't also introduce other pollutants in that process. The ultraviolet one is a little bit different, so I will talk about that in a moment separately. Just again to show you some theoretical performance of these devices. So just simple graphs to show the relationship between the air change rate, the aerosol concentration you might expect, and what you might get from a unit with different flow rates. And you'll see that it is most effective in a poorly ventilated space, so you get more bang for your buck if the space is poorly ventilated. Once you've got higher ventilation rates, you're really just not adding that much additional with your unit, and you get more effect in a small room than you are in a large room, which kind of makes sense in that you're able to get more air through it more effectively. But in a real world, the effectiveness can be a bit more complex than that. This is some labs work where we've taken a microorganism, we've aerosolized it into a chamber, we supply the air low in this chamber, extract it high. This is a room scale chamber, so it's 32 cubic meters chamber, and then we position devices either on the ceiling, on a wall, or close to the source. And what we saw both in the experiments and in some computational models, that when you position it very close to the source, on the whole you get much better results, although it's a little bit patchy here with the experiments. When you position it on the wall, again you get sort of reasonable results, but it drops off a bit. It drops off with air change rate. When you position it on the ceiling, we actually got a result that suggested the concentrations had gone up, and they hadn't gone up. What we got there is the fact it has changed the distribution pattern in the room, so we were measuring a higher concentration at our sample point. So just to sort of to show that it's not as simple as just stick one of these in and this is what you get. I said I'd mention upper room. Upper room is a more complex system. You put ultraviolet light above people's heads, and it inactivates microorganisms as they pass through that UV field. It's a very complex mechanism for how this works, but basically it's a three-dimensional field of UV light. The airflow will interact with that, and depending on the microorganism species, you'll get a reduction in the amount of microorganisms in the that are live in the air and will reduce the risk of transmission. It will depend very much on the environmental conditions. It depends on the dispersion of that microorganism. And just to illustrate some of this just shows you one of these devices in a test room and shows you the UV field that you might get from them. So you can see it's a 3-dimensional field, and it varies with particularly in the plane of the device itself. And if we model the flow, this is airflow in a room, but we can model how that flow interacts with the UV light and distributes that the effect of that UV light throughout the room. So it's a complicated flow pattern. But what we can see is if we look at some of these results, we can see that the effectiveness depends on how many device fixtures you've got. So in this room, we've got several fixtures which we can use, 2 fixtures or just a large fixture or a small fixture. But crucially, what you can see in here is that the effectiveness depends on the ventilation system in the room. So when we introduced the air in low level and extracted it high level, we got a better performance than when we did it the other way around. And that's all to do with how the ability for it to carry those microorganisms through the UV field. So just to conclude, what do we know so far? We think that close range transmission through aerosols and droplets is the most dominant route. We think that far field aerosol matters, therefore ventilation really matters in here. But we need a lot more understanding of this. How do we characterize and measure ventilation in buildings? How do we understand the importance of the different air distributions? How can we actually quantify risks and design, therefore, proper systems to deliver good performance? And we also know that technology solutions may well help, but we need to have these correctly designed and deployed for the space they're in. And as a sort of practical take home, what do we do? Well, the first thing I would be looking to do in any space is reducing and removing the source of any pathogens. So if you can stop using the space, stop people going in there, reduce the duration of time they're in there, put face coverings on people, that's your first step. Then ventilation, to me, from an aerosol perspective, is the next step. So, and if we're going to do a hierarchy of what to do in here, I would very much be going, where are the poorest spaces which are shared between multiple people? So I wouldn't be necessarily saying let's up the ventilation everywhere. I'd be saying let's go and find those spaces where the highest risks are and look at intervening there first. Everywhere else, I'd be saying let's see if we can aim for something like 800 parts per million or 10 litres per second per person. There's no hard and fast rule on this, and we don't have an exact number. We can't give an exact number that you can never make the risk zero, you just reduce it. If we've got spaces where people are generating more aerosols, we need more ventilation, but we should be first asking, do we need those spaces to even be operating like that in the first place? Another critical one is reliable and regular source of outdoor air. The spaces that worry me the most are those naturally ventilated spaces. There's no designed-in ventilation. Think about shops, think about restaurants, which entirely rely on people opening the door on a regular basis for their supply of outdoor air. And then I think we need to make sure that whatever we're considering is the systems and the human interaction with them. It's no good saying, yes, this system can deliver, if then the people in the space shut the windows or turn it off. So we need to make sure that people know why they need to use the ventilation effectively. And then given what we know about air conditioning, I think I would be very cautious about using air conditioning in poorly ventilated spaces. I think if the space is well ventilated, the risks are probably relatively low, but poorly ventilated spaces, I'd be a bit worried about maintaining aerosols in that space for longer periods of time. And then from an air cleaning perspective, look at where they're needed, where ventilation can't deliver. But when we're thinking about these, we shouldn't be looking at a blanket solution. We shouldn't just be saying we can put these in any building anywhere. We need to say, what are we mitigating? Where are we mitigating it? So what device are we having? How can we size that device effectively? What are the benefits that we're going to get? What are the risks it might pose? What evidence is there to show us it's going to work? And have we given people appropriate training and thought about the maintenance of these devices? So if we start rolling them out, we need to then do something with them and make sure they're used properly. And just to finally finish off the future of this whole pandemic's put ventilation on a pedestal like we've never seen before. We all know that it matters well beyond COVID. It matters for health and well-being, matters for all of the other air quality parameters too, matters for your mental health, your physical health, your sleep, etc. It also is one of the major determinants of the energy and carbon emissions from a building. And it's not sustainable to simply say, let's increase ventilation rates. So we're going to have to think much more carefully about how we design ventilation for effective higher ventilation rates we've had before, but now with low carbon heat for proper sustainability in there. And just to finish off by advertising, we have a new network on this where we are looking at how we can consider some of these outdoor-indoor air connections and the trade-offs, and how we can think about a more holistic approach to ventilation design for buildings in cities in the future. And on that, I'll just say a thank you to many people at Leeds and collaborators whose work is featured in the presentation today. And I'm happy to take any questions.
Thank you very much, Cath. That was
so it's a bit of a whistle stop there.
Indeed, but very comprehensive. So we've got lots of questions. We aren't going to be able to do them all, but we'll get as many as we can. Just first question is, we've got a vaccination program. How long are we going to have to do this mitigation processes, or is it with us forever?
I wish I knew. I'd like to say we can drop some things. I don't think we know yet. I think what we should be thinking is that ventilation is forever, because this pandemic, we might get it under control in a few months' time. What about the next one? So the engineering resilience of our environments should be forever. And there are certain things like maintaining good hand hygiene, which it's not really a bad thing to keep maintaining that forever.
So there will be another pandemic, whether it's something from this one or.
If you look at if you look at even the past 20 years, we've had SARS, we've had MERS, we had a swine flu pandemic, and we've got this one. And we were lucky with the others.
So in that case, then we've got to design better ventilation systems or get persuasive. Here's a typical question from an end user. How do we gain clear design to meet the future of the project? It's taken me months to get this far. In other words, how do we start to look at these metrics that you were talking about, ventilation metrics in particular? How do we know that what we've designed is safe? And how are we going to get there?
That is a really good question, because we don't yet have, how much ventilation do you need to control this? And I don't think we will ever know that completely, because there is no such thing as safe. It's always just a reduction in risk, and we will have to move to a position where we accept that there is a residual risk. It's just that we want to reduce that residual risk as far as we can. I think the comfort I've had so far is that I've not seen any evidence of significant outbreaks in well ventilated spaces. It does seem to be the spaces which really are at the end of the design space that is poor. So if we're designing and delivering to current building standards, then that's likely to mean we're in a reasonably safe position. Whether we need to go above that is a really hard thing to say at the moment.
Well, we know that actually most buildings don't meet even current building regulations. So shouldn't there be do we need a certification system to say actually this building does comply, it's demonstrably complies, so at least you've mitigated that risk? Absolutely,
and I think we do need something there. I think we need to think about how we deliver that. So it's one thing saying, well, it says 10 litres per second per person, and it's prove it's doing that. How do we prove it? So before we can actually have a certification, we need to have agreed methods of how we measure ventilation and demonstrate that compliance. And we need to think, you know, how do we demonstrate compliance in a naturally ventilated building where it will vary? Is there an acceptable number of days where it can't deliver, or should it always have a particular ventilation rate, in which case you would need a hybrid system?
How are we going to get to that position? Because it's one thing to say we need to have this, but how? Does it come from the industry? Do we say, actually, we think it should be this?
I think it comes from a collaborative effort. I think it needs to come from the industry, from the research bodies, base, and from the policymakers. And I think it needs to be a collaborative approach. And I think we need to recognise in there that there's no sort of single hard value that we can give, that it's going to have to be, you know, some form of discussion point. I mean, CO2 is a really interesting one. I know in Scottish homes, I think they have CO2 monitoring included now. In many buildings we do monitor, we use CO2 as the metric for controlling ventilation. We just don't display it, we don't record it, it's all just hidden in the BMS somewhere. I know I think it's in Belgium, they tried to introduce CO2 as a measure for buildings. But the minute you say it, so I think they said it might have been 800 parts per million. I can't remember whether that was above baseline or not. So if the minute you put a number in, you have to then say, well, how do we demonstrate around that number? What if we go over it? If I said 800 parts per million, what do we do if it's 850? Is that just within the tolerance or not? What do we do if it's 1,000 but it's only there for 30 minutes? Is that breaking it or not? So we have to have a really clear understanding of what is acceptable and what is not, and how much you can go over something before it becomes poor.
We've had this debate in our well-being group for a long time. If it were dirty water, you wouldn't find it acceptable, but because of dirty air, you don't notice it. So you need the equivalent of a canary in the cage. And are you saying that CO2 is effectively that?
I think CO2 is, as long as it's not taken as an absolute hard value. But I think a lot of buildings, it can be a useful canary in a cage. I think the other problem you've got is, unlike your water, so your water is a single supply to your building, whereas in your air, you're now dependent on the quality of the outside air as well as what's inside your building.
Oh, indeed.
And you're very dependent on human behaviour. Your water supply to your building has very little dependence on human behaviour, whereas our air does. People mess it up all the time.
They do indeed. In fact, the point about that, and the two things are intrinsically linked. You could deal with one while you deal with the other. And the Environment Bill has been delayed for 6 months, or a further 6 months. Could this turn into a blessing in disguise, in that we could also bring forward measures to deal with COVID or pandemics, and deal with exposures to PM 2.5, NOx, ozone, and other air pollutants? Do you think there will be a connection between the two?
I think there are opportunities, and certainly I know the building regulations is out at the moment. The Part F is out for consultation at the moment, and that one, there is a move to think about how do we make sure we incorporate the disease transmission risks into that, you know. And you know, a document that goes out this year won't be perfect, because you know, we're trying to draw on a limited set of evidence, but it will be better than what it was. But I think, again, it's the gap between what we've written down in a piece of guidance or standard and how it's actually delivered in practice. And that's where I think, you know, we've got buildings out there that don't just not meet current building regulations, don't meet anybody's building regulations of any standard ever. They've got no designed ventilation at all. How do we deal with that? And we can't just say we're going to close all those buildings, because some of them are critical spaces. So we have to recognise there's got to be a plan forward. I mean, this maybe is where some of the air cleaning comes in. I think it's not necessarily a long-term solution for those buildings, but it might be the sticking plaster solution that we need to get those spaces more acceptable in the short term.
In Germany, they've started retrofitting classrooms with ventilation systems. Should we be doing that in the UK?
quite probably. I think, I mean, we need to be first of all understanding where are the badly ventilated places. So there's a lot of noise that places are badly ventilated. We've got very little hard data. I'm sure there are some very badly ventilated classrooms, but I also know there's some very well ventilated classrooms. And this year there's some exceptionally well ventilated but very cold classrooms.
The old Victorian ones probably quite well ventilated.
But even some with the more modern systems in that have been designed correctly are delivering what they should deliver.
So, I mean, this is the sort of thing that SAGE should be doing, is it? Why haven't you come up with something on SAGE to deal with this?
So, yeah, so this is a common question. Why haven't SAGE done this? And I think this is a common misconception about SAGE. So SAGE are there to give advice to government. And most of the advice they give is in response to questions from government, which is sometimes why people look at it and think, well, why did they do this? But that's because that was the question they were asked. But SAGE is only an advisory body. And bear in mind, it's a relatively small group of people who are trying to deal with an awful lot at the same time. So it can't actually change policy. It doesn't make policy, it gives advice. But if things actually do need to change in buildings, that is policy makers who make those decisions, and then they need to put that out to the industry. It's not SAGE who make the policy.
Final question, and I'm sorry for everybody who's asked questions, we've not been able to deal with them, but will a drive for net zero or changes in the Building Safety Act make this even worse?
I hope not, because I hope that people have recognised early enough now that ventilation is really important. I mean, you know, there is a risk that we try and deal with net zero by simply sealing up more, and that can't be the solution. But I hope that enough people have recognised the importance of ventilation over the past year that won't happen. I think we all need to keep a close eye on it. And I think, again, it's one of those things. It's much easier to demonstrate the energy performance of a building than it is to demonstrate the health and well-being of its occupants.
Cath, Noakes, thank you very much. I'm afraid we are out of time. It always slides by.
Apologies, I talked.
No, you told us an awful lot. We always take the questions that we don't answer onto our LinkedIn group, and I know you're very busy, but maybe you or someone in your team could just engage
I'll
in
try
that.
and look in and have a look and see what else is in there. And
there's some very good questions, but I'm afraid we just haven't had time to do it. So thank you very much for giving up your time. We know you're very busy, and that was very, very helpful, very informative. And I'm sure it will be watched on the record basis an awful lot of the time. So thank you very much, Cath.
Thank you.
Okay. So actually a quick plea, if you are an academic and you're watching this one, you've got some research you think our members or a wider audience would be interested in, get in touch, because we can give you a platform to discuss that. In terms of what's coming up, on Friday, we've got the Construction Playbook, which is a really, really important government initiative with Fergus Harradance, who's Deputy Director of Construction at the base. That'll be a fascinating one. Book early so you don't miss your place. If you enjoyed this, tell people. Join that discussion on LinkedIn. Become a member. You might learn something you didn't know, which is the basis of us. On that note, I'm going to say thank you very much. Thank you very much to Claire, who did her first production in probably 9-10 months. No hiccups, Claire. Great, thank you. Have a great lunch, and we'll see you on Friday.